So this is the second video about semantics for parallelism, and it will be a bit deeper and start to study the semantics of parallelism with a few generalities first, and then a study of two constructs for parallelism. So if you have a look at what exists as semantics of parallelism, this list is not exhaustive, but it's the main thing you encounter when you look at articles. So as I said, one of the main way to do parallelism is to have shared memory between threads. There's not much standard semantics with deep studies here. We'll see one solution later in this course adapted to mini-while. Um, Writing a semantics for shared memory is not difficult. Uh, Having interesting properties on these languages is more because by nature you end up with a lot of different behaviors for the same program. So additional constraints on the language, like restraining what kind of shared memory you can have, or logic showing that some parts of the memory is not shared, for example, or static analysis is necessary to prove interesting properties. And there's quite a deep study about that. Mostly there's a lot of studies on how to add something to the semantics so that you have something interesting about shared memory. Message passing have much more classical calculi and it's easier to identify major solutions in the semantics to encode message passing, like with languages like CCS or calculi like CCS or PyCalculus that are highly studied. And there's also automata-based formalism that can be considered as message passing. I'll show you just afterwards what CCS is, and I'll discuss a bit more, and you'll see a bit more what happens. Then there's plenty of models for high-level programming. Is it calculi or languages? Generally, it's calculi in the sense that it's not a full-fledged language, but it's bigger than what you would know as lambda calculus or PyCalculus. It looks a bit like what we have for mini-while in the more complex cases. But as there's plenty of different ways to do parallelism, there's no single calculus that is minimal and highly studied, simply because a lot of different models for parallelism exist, and it's difficult to rank them or to consider some of them as better or less good than others. They are mostly adapted to different forms of parallelism, so different problems. Okay, before getting into one real semantics, okay, what kind of semantics do we see for parallel programs? So we've seen that there are different kind of semantics, big step, small step, denotational. First, there's in general no big step semantics for parallelism. The reason is that big step semantics takes a program as a whole, and parallelism needs to split the program into pieces to compose and interleave the semantics of these pieces. Denotational semantics does not exist much neither. There's a few trials, but it's difficult also because somehow, in general, denotational semantics is big step. In more recent research topics, you could encounter some form of smaller step approach to denotational semantics that could be considered as a good way to have parallelism. So here we'll do quite standard things and we'll do small step semantics with interleaving between the small steps. Basically, the idea is that if you have two pieces of the program, P and Q, P that can do several steps, which would becoming P1 to Pn, and Q that can do several steps, becoming Q1 to Qn. Then we consider that P parallel Q does a combination of the two, so doing sometimes the step of P, sometimes the step of Q. And we have a simple rule for parallelism that is very often used. So the standard rule that generally expresses parallelism in the semantics is to say that I can have one process P that becomes P prime, and in that case P put in parallel with something else becomes P prime in parallel with the same thing, and that's how you will have interleavings. And you just need to allow reordering of processing, saying, oh, P parallel is a commutative operator, so I can always take a process and put it first so that it's reduced. So most of the time it's sufficient to have this kind of rules, and that's what we rely on in this course. It's still sometimes a bit limited. You don't express things that are not directly related to the interleaving and the fact that perhaps you need a bit more information on the history of the operations like you have in memory models, and you don't have much notion of true parallelism saying, oh, those two happens at the same time. It's not really true because in CCS we will see how to have two threads that communicate and that synchronize, but it's more a notion of communication and synchronization than a notion of true parallelism. We will now show different operational semantics for parallel constructs, and I will start by showing you the semantics of CCH, which is a calculus based on communication. CCS syntax looks like this, so now you should be a bit used to the syntax that we present in semantics and calculus. So it's based on a few notions. We suppose we have channels, and those channels have names, so we'll call them A, B, C. And those channels will be able to transmit messages. For each channel, you have a codename for the channel, in the sense that you have A bar that corresponds to the A. So you could consider that A is sending something on the channel A, and A bar is the action that consists in receiving something in this channel. CCS is very simple, and there's no data transmitted, so there's the sending and the reception is completely symmetric. If you send data, then data transmission makes the sending and reception even non-symmetric. As it's fully symmetric, you have it's a complementary. You have A bar bar, which is RA, so which is always convenient. And you suppose that you also have another kind of action. So those ABC are names of channels, but in fact, A could be at the same time the channel A and the sending on A, or the reception if you prefer. Among actions, you have three kind of things: sending on A, reception on A, and to, which is a non-observable silent action. You can see it as a local evaluation inside the process, for example, on anything you don't want to observe. So based on those actions, we can compose processes. So we have in action an empty process. Not much interesting. We have the prefix operation, which is a dot. And so this says I first do an action mu, and then I continue afterwards with another process p. Mu is defined just above here. Then we have the parallel operation that just input in parallel two processes, p and q. And a bit similarly, we have the external choice p plus q, which behaves either as p or as q, possibly in a non-deterministic manner. We have a restriction operator that takes the name of a channel A and says, no, A is a private channel for P, meaning that inside P, sub-processes can interact on channel A, but not outside P. The name of channel A cannot go outside P, outside the new A. So we call this new A. We have an operation for recursion. So it's a process P with definition K equals P, which means if I encounter the variable K inside P, I would recurse again at the beginning. And you can define process names. There's a bit two different ways to define CCS. Either you have the recursion operator, or you can define a channel name like in P equals something, and then you don't need the recursion because you can use P inside. So that's just a choice. I mean, both are equivalent in terms of expressiveness. It's not exactly the same way to express the semantics. So what is the intuition behind this syntax, and what is intuitive semantics? First, the semantics of A.P is I offer action A and then I become P. The semantics of A then P plus B then Q, it's an external choice, as we said. So either I do A and then I become P, or I do B and then I become Q. New, I told you before, it's a process that exhibits any action of P but not A. A stays inside P. The vertical bar is the parallel operator, so it does the action of P or the action of Q, but also if P offers A and Q offers, it should be A bar, for example, then they may synchronize and produce a two action. Parallel not only allows you to do the interleaving, but also allows the two sub-processes to synchronize on an action. To write the semantics, we will use label transition system. So here we come. What is a label transition system? It's a system made, it's a kind of a graph, it's a system made of nodes, and between each nodes I have edges, but on the edges I have labels. So I have transition between states. So this is a state, and between those states I have transition. This is the arrows, and on those arrows I have labels. So if I consider the process here, and so it says I have in parallel something that emits on G and something that emits on A and then receives on C and receives on G. So at the beginning I can either emit A bar, or here I should add emit G bar. So we complete it together. Then after I've done A bar, I can still do G bar if I didn't do G bar. And then I can do C, then G. And if I reach G without doing G bar, I do G bar. This is not complete because, of course, here, if you do this way here, you should do an A bar because you can still do the A bar and so on and so forth. So this is a label transition system. Okay, so let's go a bit further and we get another explanation, and then we'll switch to the semantics itself. This is just a semantics to show an example, mostly to show what is a recursion. I said recursion introduces the name of a variable and you can reuse it. So if you consider rec c1 tick.c1, it produces this label transition system that can do a tick and then becomes the same process again, so it can do tick again. So generally you could put C1 as a label for the state if you want. So it's a label, so globally the label transition system is a label graph where vertices are process expressions, the labeled edges are transitions. So here I have C1 as a process expression, tick as a transition. You depict each derivable transition of a vertex, and then you abstract from the derivation transition in the sense that you don't show the detail on how you protect your transition, you just label with the action taken. I got a small question that is, do you see what are the possible traces or output sequences of this process C1? I leave just a few seconds to think and I'll write it here. Tick is a possible output sequence, but also tick, then tick, but also, and you get it until it's tick, any infinite number of ticks. Here's semantic rules, which are split in two slides. On this first slide, we'll see action, communication, and parallelism, and the more advanced features kind of on the next slide. First action possible, as I said, when you have an action prefix, you can just do the action and you become the rest of the process. So this exactly corresponds to mu p becomes labeled by mu p. So this is the form of your label transition system if you see what you had before. Communication is when input and output match, and that we didn't show it on the examples, but if you have a process P that can emit an A and a process Q that can emit an A bar, then they communicate and they become the resulting process P prime and Q prime, and the resulting action is tau, which they synchronize. You have basic parallelism that allows you to do reduction on one half of the parallel operator. If you have P parallel Q, then P can reduce it. according to its own semantics, and same thing for Q. Then you also have non-deterministic choice, remember, so it's a plus operator that says, oh, I either do P or do Q. So if I have P plus Q, I can just follow the reductions from Q. This is true only if Q can be reduced. So if, for example, it's a communication that cannot occur for some reason, then Q will not be able to reduce. It might be P that does. So it's a non-deterministic choice, but provided the chosen process can do something. Scope restriction is very simple to express. So this gives a private channel A for P, meaning, oh, if P can do something, but this something does not speak about A, then P can reduce without doing anything. But if it was on A, then it cannot be visible this way. A can only be used inside P. And finally, we got the recursive definition that says to reduce rec variable k on P, I should reduce P where the variable k is replaced by the recursion itself. In other words, wherever you find k, you would replace by the whole thing. Now, I suggest to switch to a small example that we will do on paper together. And so what I will do is that I will show you on the tablet how to derive one possible behavior of that process. And finally, I will ask you to your opinion on whether the following triads are acceptable for this process. So we'll derive together one, and then you'll try to see if the other ones can be derived or not.
So this is the rule for the evaluation of the CCS term that we have on the course. I guess you have tried by yourself. If you didn't, I suggest you would do it now. And what I will do is that we will try with how we can apply which rules to reduce this term. So we want to find a rule that allows us to reduce this here. And as it's a new A operator, I don't have the choice. I must apply the rule for restriction, which is the rule that is on the previous slide. So you should have the previous slides at hand. And it says, oh, it's a new A with some term P. So P is this big thing. And I must see what I can do. I cannot do A, and I cannot do A bar because A is restricted. So in fact, the only option is for A, for this term, to do a toe. How come? Because here we can do a com rule, the communication rule. And this works because A, B can do A and become B. This is done by the prefix rule. And this other term can do A bar and can become several different things, but let's suppose it wants to become B because we'll see it's possible. Bar. How can this become B bar? Is because we must apply anyway the choice rule, so I'll denote it plus here. And let's say I choose the term from the right, and it says, okay, then I want A bar, B bar, so it's the second rule for choice to become B bar by A bar. Indeed, this is the application of the rule for prefix. So here I chose this term in the sum, and I obtain this and this. So by 2, I have B parallel B bar. To apply restriction, I must check that 2 is different from A and A bar, which is the case. That's why I choose 2. So here by 2, I can become B parallel B bar with still the restriction. Okay, so this is the first application. Now we can try to start again from this term and continue the reduction. So we start from this term and we want to see what rule we can apply. It must still be a restriction here. And we can check that by restriction, I could decide to do B, which is different from A bar. And so I want B parallel B bar to become by B something. And this is the application of the parallel rule, which is 2 slides ago, if you have a look. So it's parallelism rule. And it says by B I can become, so B becomes the empty processed by B. So yeah, you can always say that for anything that A is the same thing as A dot 0 if you need it. Okay, and this becomes 0 parallel B bar, and you have the other thing that is 0 parallel Q is the same thing as Q. So this becomes new A B bar. And we could do the same again, which is even simpler. You can check by yourself that new A B bar reduces to 0 by doing B bar. It's by restriction and prefix. I let you find out this one, it's easy. Okay, so globally the whole trace here would be 2, then B, then B bar. So this is a possible trace for this. Okay, I guess you got the possible reduction here. So we did 3 steps, 1, 2, 3, and we used a bit of equivalences. And so that's one possible reduction and one possible trace for this term. And the next exercise is to try to find which of the others are possible, but I let you do that, and we'll discuss this during the course if necessary.
So we had the first semantics of one parallel construct, which corresponds to message or to communication. I show you a second construct that you can find in the literature, which is futures and their semantics. So let me first explain you what a future is in the context of messages. So suppose you have different entities and they communicate by messages, but not like you had before, where sending and reception is synchronous, more like A can send a message to B, it's a request, and B will deal with the message later. You might want to have a result for the message. So in that case, you would call the request because it's something that requires a reply. And in that case, you might want to tie it closely the reply to the request, not as another message, but as a specific entity. This is what a future is. A future is an empty object that represents the future reply that will be given by B. So how does this work? When B will deal with the message, he will produce a result, and at this point in time, the result will fill this empty object, and now the empty object will be filled. We say that the future is fulfilled. And you can see from the side of A that A can send a message, he can do other things while keeping a reference to the future result. And at some point in time, he can get the result, that is, access this future. So that's it. A future is a promise of a result that will be computed. So that's in a message-oriented setting. You can also use futures in a more thread and task-like setting where A could spawn a task, and the task, when it's finished, it will compute a result that will fulfill a future, that will fill the empty object. So that also works. This is what we will see here, calculus that uses futures and have basic tasks. So what we do is we take a simple lambda calculus and just add futures to them. So the idea is that we start from a lambda calculus with its 3 possible terms. Lambda abstraction, which is the definition of a function that has x as parameter and e as function body. We can have variables inside terms and function application that is e prime that applies the function e with the parameter e prime. So it will replace the x inside the function definition by e prime or the evaluation of e prime. We add to this simple classical lambda calculus two constructs that can be written by a programmer and one element that arrives at runtime. The first thing that programmer can write is async of e, which means evaluate the term e asynchronously. So it is supposed to represent the fact that a task or thread is spawned, and this thread evaluates the term e, and it creates a future immediately, and it will fulfill the future when the evaluation of e terminates. To check that an asynchronously spawned task terminates, we have the get of e construct that takes as parameter something that should be a future, and what this does is that it waits until the task that corresponds to the future terminates and fulfills the future, and then get of e is replaced by whatever is inside the future. Last thing that can appear inside lambda future terms are references to futures, future identifier. Those only appear at runtime, and they are created by the async of e primitive. So f only appears at runtime. Sometimes we might need to know what a value is. So a value is whatever is fully evaluated. So it's either a future identifier or a lambda abstraction. We could also add other values like integers or booleans. That's how my terms, my programs look like. We'll do like we did quite often in our semantics. We have a different setting at runtime. At runtime, we'll have configuration that is built from terms. And what is a runtime configuration? It's a set of futures, which is a set of elements. Some terms are fut of f, which means the future f has been created, but it's not resolved yet. Fut of fv, which means the future f not only has been created, but has been resolved. So the task that corresponds to this future terminated. And we have tasks, which are basically elements of the lambda calculus, except that each task is here to fulfill a future. So we also have recalled futures inside task. So what is the semantics? So semantics will explain how to reduce from one configuration to another configuration. So inside semantics, we first have the classical lambda calculus. So the classical lambda abstraction would say, if I have somewhere lambda x of e applied to v, then this is the same as having the term e where the parameter x is replaced by v. For the moment, don't look too precisely as e, just consider this as this is a task that is supposed to fulfill one future. Consider for the moment e as meaning somewhere inside the task I have this, and I'll come back to this in the next slide. So what does it mean to create an asynchronous task? It means that same thing inside the task, somewhere I have a place where I want to do this async of e statement. So look at this for the moment, and the rest is kind of the context that is around. And what does this mean? It means, oh, I want to create a future, and for the moment the future is not yet fulfilled. Then I want to create a task that is supposed to fulfill this future, so that's the syntax for this. And now the task for G just has done the asynchronous creation. You just record here that f is the name of the created future, so I can refer to it inside the task that spawned the asynchronous task. This context simple rule just means that you can evaluate whatever subpart of a configuration, and it works because we also had the constraint that configuration is identified modulo reordering of tasks and futures. Okay, so I've done almost everything except that I never fulfilled the future. And how do I fulfill a future? Well, if a task fitting future f is finished, and how do I check if it's finished? It's a fully evaluated value. That's how I check that the task ended. Okay, so if it's a fully evaluated value, and of course I must have an unfulfilled value future for this task, which is always the case in practice, then now the task disappeared because there's nothing else to do, and the future is changed into a fulfilled future, so there's no more unfulfilled futures. Last thing is how to synchronize on this fulfillment of the future. Then that's the meaning of the get F statement. The get F statement says, oh, I'll check that the future is fulfilled. So that's like exactly the fact that inside the configuration, there's a future F, and this future has a value V. And which has a value V, then the access to F just replace reference the get F statement by a V, which is the value stored. So it just checks that the future has been fulfilled and replaced by the value. If the future has not been fulfilled yet, you understand that this task here cannot do anything. It's blocked here. It cannot continue. At least it cannot continue at this place. But we'll see that we'll write the set calculus, the E construct, so that there's a single place where I can do something. So yeah, configuration identify model wording of tasks and futures. And the only thing I didn't explain you in this slide is what is E. I'll come to this in the next slide. E is an evaluation context or reduction context, sometimes called too. It's used to focus on part of the configuration and reduce this part only. It's a tool that is used in several different semantics, the one that are a bit more evolved, because it's a good way to put aside part of the configuration and restore it just afterwards. And it gives a lot of control on which part of the configuration can be put aside and where the reduction can appear. So if you compare it, for example, to context rules here on the previous slide, the context rule was working well for just putting aside future and tasks, but putting aside part of the terms, it wouldn't be very convenient in our context. So that's what we do here. For lambda calculus with future, we define E as something that looks like this. So it's an expression with a hole. There's always one hole inside the evaluation context, so you do not need that. So basically, E is just an expression with a hole, but there are special ways to construct it. The hole can be either on the left part of an application with whatever you can have on the right. It can be on the right part of an application, but the left part should be already evaluated, so it enforces the evaluation from left to right. And here you see the kind of things you can express easily with evaluation context. Or else it can be inside get. So you can evaluate expressions inside get. You notice, for example, that it cannot be inside the async, because the async means I want first to create a task that will later do the job. And how do I use it? It's very simple. So if you look at the semantic rules, you had something like here E of the application here. And you just put E bracket something, and this just means E where the dot is replaced by the small expression E. So if you have a look at a classical lambda calculus term, this allows you to split the term into the blue part, that is a reduction context, and the red part, that is a reduced term. So E here would be this thing, and inside E you would have a big dot here. And the operation of context instantiation will replace the dot by this term. To finish with, I'll show you an example of a lambda fit evaluation to illustrate the semantics and show you how it works in practice. But first, as usual, we need to create a configuration from a program, and a program is just a term E. So I want to create a task that will evaluate the program. So the initial configuration for a program E here is just a single task that will fulfill the future F. You don't care about F because it's a feature that will never be used, but it's a way to create a configuration, and E is the program itself. So the question now is, what is the behavior of this program? You will check what rules you can apply to the term task F of and this big term here. I will do this on the tablet, and I suggest you first do it as an exercise.
So let's try to evaluate this term. And to evaluate the term, we must place it in configuration. So what we said is that a good configuration is a task that corresponds to a fresh future f and to these big terms. Okay, so now we can start the evaluation. The good thing with this semantics, so you should have a look at the semantics of course at the same time, and if you look carefully, there's not many premises except for the context rules that should enroll several things, but it just goes at a single place in the configuration. So I'll omit the application of the context rule, which will allow me to write the semantics in a linear way, which will be more adapted for our case here. So here, I won't write premises, I will just directly do the thing and not below what's necessary. So inside the configuration, there's a single term here, so of course, this is the part that will be reduced. And the first reduction we could apply is the red lambda, I'll call it lambda 1. And it's applied, in fact, so inside this, but applied to the case where E is this, and this is the value V. Indeed, this is a value because it's a lambda abstraction with E inside, and this is the V. So it gives us what's inside, lambda Z dot Z, still the same task, F, but inside we have now lambda Z dot Z. So we have this term where X is replaced by 3. This is just classical lambda calculus reduction. Okay, so now we get to the second step. So we still apply the configuration is still made of a single task, so this is where we apply things. But now we will apply the async rule, because the left part is already a value, so we can go to the right part, and a valid E evaluation context is E equals this, and what's inside the evaluation context is this. And this is exactly what you need for applying the red async rule. And for applying the red async rule, you need a fresh future, so we'll say that G is fresh. In that case, if you look at the red async rule, you obtain this task. We take again the E, so D lambda Z Z, and we replace what's inside the box, the evaluation context, by G is fresh, so by the future G. So this is the current F task, but this spawned a new task. So if I was in order, I would have started by fit of G, that is still undefined. In fact, I did it the other way around, but that's fine. And the task for G is the expression E, which is inside the async, of course. So it's lambda y dot y plus y applied to 3. So if I compare to my rule, if you want to do it again, this is the expression E that goes here, and these are the three tasks, and of course F is G in the rule and G is F in the rule. So then I have applied this async rule. I can go one step further, and now I have a bigger configuration, so I could do different things. I could apply reduction to different tasks that are ongoing, in fact. So I could choose different parts of the configuration. Let's suppose in the next step I choose this one, which is an easy one. So by lambda evaluation on this term, I would find task F where I apply lambda reduction to this term, which is lambda ZZG, so it gives me G directly. Okay, and this term I cannot evaluate it further, But what I can do is, of course, then I also have fit of G and the other task. Now I can try to evaluate this task, to progress on this task. It's also a lambda abstraction, so by lambda it gives me, so the first is unchanged, and the last task is okay. I just applied the lambda reduction rule, and so it makes 3 replace y in this expression, and it gives me 3 plus 3. I should have a rule for plus, and I will obtain task G6. And what's more interesting is that now I reach to the end task rule, because this is a value, and if you look at this, it's exactly what I need to evaluate a value. I have a fit of G, and I have a task G that has a value. So it stays on the future and on the task, and it just says, okay, now I still have the task fg, which was untouched here, but now the future g has a value which is 6. And this finishes the reduction. I didn't illustrate all the rules. It would have illustrated all the rules if I had a get statement here. And if it was the case, the other things would have been done the same way, but here I would have reached not this, but instead the configuration, and this would be reduced by the get rule into now 6 is computed for the task F. And the future G is still here because several tasks or several parts of the term could have a reference to the future G, so it should not be removed at all. And so that's it for this reduction.
Before finishing this video, I just wanted to show you what looks like semantics that is a bit more complex for futures. It's just an extract of a semantic that has futures, a bit in the style of lambda calculus, but has also states and communication. So it's a bit more realistic language, if you want, that would look like an actor language or language that with entities that communicate and have futures. Of course, it's too much complex to be studied here. This concludes this video, and next we will see how to add parallelism to mini-while. So we'll do new semantic rules, but based on the ones you already know for mini-while.